chairs.
Okay, let's go ahead and get started. On Fridays, normally what I'm going to do is make this kind of like a help day to make sure we catch up on everything, right? Because we've pretty well covered everything in logic. But there is one thing I did want to show you to kind of help you see the consistency across different studies. One of the things you learn about learning itself is that learning is experiential. When you see something or learn something, you compare it with something you already knew. And if you make that tie with something you already knew, then it stays with you for a longer period of time. So, I talked last time about logic being an algebra. But let's go a little bit deeper into that, because I think this will help you. It may also help you when you're coaching others. Some of you will be parents someday if you aren't already. And I don't believe, this is a political statement, I don't believe that the public school system does a good job at teaching math. Okay? Do you agree or not agree? Agree, but want to be secret, right? Yeah.
Yeah.
All right, what a statement. Yeah, I get a lot of agreement on that. So, just like learning a new game, the first thing you want to learn are, what's the basic rules of the game? And are there simple rules to get started? If you were to play any of the games that we get today, don't you want to know the object of the game and some of the simple rules about moving around in the game and some of the things you can do in the game? So algebra is the same way. And in fact, it's all based on 5 rules. And every algebra is based on these 5 rules. Anybody want to guess what they are? You probably heard them in elementary school, and then nobody reinforces them. And part of learning is reinforcement, isn't it? Okay. So the first one, this will probably jog your memory. The commutative law, or axiom. Now the reason it's an axiom is you don't prove these. These are given from the very beginning. It just says this is the way it is. We don't discuss why it is. This is just the way it is, right? Just like rules of the game, right? Does anybody know what the commutative law is? Or axiom? I forgot.
When you're adding between multiple numbers, it doesn't really matter in what order you add them. Same with, I think, multiplying.
You've got it. Yeah, you're very close to it. And it comes from the same word as commuting. So how many in here are boarders? You got some boarders? Not very many. So all of you then are commuting to school, aren't you? And when you commute to school, you go from your home to school, and at the end of the day, you go from school to home, right? Probably the same distance, unless you take different routes. Right? It's kind of like they're equal. And all the reason I do that is that's that experiential thing. I want you to see where these words come from, because then you'll remember them, okay? So, yes, it says that A plus B is equal to B plus A, and A times B is equal to B times A. Okay? Now, second rule. The associative. Now, the associative actually is part of what you were saying too. Okay? What about if I have more than 2 things? What if I have a list of things? When you pay your bills at the end of the month, does it matter which order you pay them in? You still end up with 0, right? Left over. Anyway, yeah. The order in which you do things does not matter, does it? So, A plus B plus C is the same thing as A plus B plus C. And the same thing with multiplication. A times B times C is the same thing as A times B times C. By the way, these things are not intuitive to a young person learning math for the very first time. If I had 5 marbles and somebody gives me 2 more, that's a different scenario than having 2 marbles and somebody giving me 5 more. And until you do it a few times, you don't realize you come up with the same answer. And especially over here, if I have 2 sets of 5 marbles, is that the same thing as 5 sets of 2 marbles? Yeah, you have 10 marbles either way. It's not intuitive. But we know it, so we've been doing it so long, you say, okay, that's true. But those are rules. The distributive. And the analogy I use here is dealing cards. When you deal cards, you're distributing cards, right? And you distribute the same number of cards to each person. So the distributive law multiply, you can distribute that multiplication across the 2 added numbers. Can I go the other way, by the way? Is the distributive law a one-way rule? No. Is there is that rule legal? No. Okay. So in the mathematics of numbers, distributive law is only one way. And it's called multiplication over division. I'm sorry, multiplication over addition. Okay. There's the identity. And in a world where identity theft is such a big thing, it's a good way of thinking of this. Not a good way, it's a negative thing. But if I have the number 2, what can I add to 2 so that 2 still remains 2?
Yeah.
0, right? So we call 0 an identity. Because when you add 0, you don't change the identity of the number. That makes sense? And it's a universal identity. I can add 0 to anything, and that anything still stays the same, right? But here's something interesting. There's more than one identity. What can I multiply times 2 so that 2 stays the same?
1.
1. Oh, that's interesting. And then there's one last, and I alluded to this the other day, called the inverse. And it involves the identity. So what can I add to 2 to get 0?
-2.
So -2 is the inverse of 2, isn't it? Oh, that's where subtraction came from. It was because with the counting numbers, we couldn't introduce the concept of inverse to people in elementary school. But that is the actual law. So 2 times what equals 1? What's the inverse of 2? And we actually use the term inverse. Anybody? 1/2. And that's where division comes from. That's why division is really part of multiplication. Subtraction is really part of addition. There are only 2 operations. Now, why did I bring this up if we're not studying numbers? Because we're studying sets. We're studying logic right now, right? So, let's look at logic. Let me put this on mute for a minute. Because this will also hold true for sets. true that two propositional statements connected with an and are the same no matter which order we put them in? Today is Friday and we are in 161. We are in 161 and today is Friday. Same thing, isn't it? Okay. And by the way, aren't those the same also? Or statements, doesn't matter which way you state the or, it's the same. But what about this? Yeah, it doesn't matter how you list ands and ors either, does it? Now we list ands probably more than we list ors, but ors are options. And if I have three options on a screen with bullets that I'm going to click on, right? Does it matter which order I choose them in? Normally you choose one because it goes to another screen, doesn't it? But you see what I'm just saying? It doesn't matter which order you put them in. How about distributive? This should be R. Are those equivalent? At this point, you probably say, I'm not sure. I'd have to play with that for a while, right? The answer is they are. But here's something interesting about logic. The distributive rule goes both ways in logic. Goes and over R and R over and. Now, I was talking last time about electrical circuits, and some of you are going to get into hardware a little bit. If you get into circuits, this is a rule for simplifying circuits. These gates, the P gate, is repeated in this statement, isn't it? That means there are two transistors probably doing the gate. But I can simplify it by knowing this. Now I only had one transistor. All right? Now this is a simple example, but you can imagine if you knew all these rules and you combine them, you could get a very complex system and get it short. Now what about a multi-functioning device that is combining two different devices? For instance, well, the cell phone's a good example of it, I guess. It combines videos from which I may have had a video player at one time with a music player, or maybe a telephone. That's better. That's just something very different, okay? Now, as I was trying to come up with the circuit design for a cell phone, I take this device and I take this device and I compare them. Well, first of all, they both have a voltage input, don't they? Do I need two separate voltage plugs to charge these things and use them? No. I can now combine them into one. There are probably many other things within the circuits, though, that I could combine into a simple circuit, or simpler circuit. And that's where this comes from. That's what people use it for. What do we call this when you're in a terrible old math class and you're having to do a lot of that kind of stuff? Do you remember what those were called? Proofs. Yeah. And proofs is the last topic we're going to talk about in class today. Not today, but in this course. And the reason is the math version of this course does everything with proofs. But what does proofs do for you as a computing person? It helps you develop software. Because when you're developing a program, when you go back and look at it, you might look at it and say, I could simplify this a lot. And it's just the process, not the rules necessarily here, but the process of knowing that you can look at a whole bunch of stuff and see similarities and begin to pull them out and share them and simplify your whole logic flow. That we really do proofs. But we're going to do it as a separate section at the end of the course rather than all the way through. But this is distributive. Well, here's something interesting. What about identity? What can I AND with P such that I end up with P? Now, it's not the statement itself. It's the truth value of the statement. So if P was true, what can I AND with it so that I end up with true?
Tautology.
Yeah, you want to make it a tautology, don't you? So what can I put here? A T. Now let's look at it. If P is false, false and true is false. If P is true, true and true is true. So when you use T in an AND statement, this is what is the value you're going to get, truth-wise. It's going to be the value of the P. If P was true, it'll stay true. If it was false, it'll stay false. Does everybody see that? Well, then you have to ask yourself, so this is going to bend your mind a little bit. Can you come up with what you need to OR with P so that P stays P? In other words, the truth value of P.
Anything?
No? What would you guess? If this was T, what do you think that is?
Not T.
False. Yeah, not T, which is false.
Like inverse.
Yeah, I did. No, I'm talking about the truth value, not the unknown.
Oh, not the little.
Yeah.
Okay.
It's not like the X and minus X. So, but you were on the right track. This is the identity, not the inverse. So, P or false. Now, remember that an OR statement is only false when both are false, right? So if this was false or false, you would still say false, right? Now, what happens if P is true? A true or false is true, isn't it? Interesting. Okay. So what about the inverse? What's the inverse of P? Not P, right? So, what is P and not P? What's the value of that? Truth value. Well, it's always going to be false, isn't it? Because one of these two is going to have to be false, isn't it? Doesn't matter which one. If this one's true, that one's false, and this one's false, that one's true. And with an AND statement, if there's one of them false, the AND is false. Now that's interesting because with the AND, I got the identity for the OR. So what about P or not P? It's always true, isn't it? Because one of these has to be true. With an OR statement, if at least one is true, the OR is true. So what I'm trying to do is kind of open a window for you into why logic can be a whole semester topic. And there could be some fun things in it. I took it in a philosophy department rather than in the math department, although I was a math major. And it was very interesting to learn it in the philosophy department. But it is definitely an algebra. And the basic rules of logic are commutative, associative, distributive, inverse, identity, and inverse. Okay? All right. So, I just want to make you aware of that. And of course, now it's on video, so if you want to go back and look at it. By the way, have you seen the videos from earlier this week? How many have seen them? Okay. They're in the modules, so So it's in the module under Logic, and it's called Lecture Video or something like that. And those, I made a video on Monday, but I forgot to set the camera right. And I had it on telephoto or something. All I got was my feet. So, see, I get nervous on the first day too. So, Wednesdays, which was 2 days ago, that's the one that works. And that's the one that's now up. Now, I think there's a previous, I know there's a previous video that I actually made in my studio at home, which is like 2 or 3 years old. So I'm trying to refresh them periodically. So I'm going to be adding new videos probably this semester as we go. Okay. Now, something else I want to congratulate you guys on. You all, there's a good return now on people trying the quiz once. And those that took the quiz, did you find some value in struggling the first time through? You found out what you didn't feel comfortable with? So what we're going to do today is go over any questions you have. Now those that didn't take the quiz, yes, you're going to see some answers today, but is that really valuable to you? No, it's not as valuable as having struggled with it once, because then the answers are going to be more of a, aha, that's why it works, okay? So please, as we go forward, try to make sure you do the quizzes once before the next class. And you'll notice that we have 3 classes a week, so that means there's a Wednesday and a Friday to go over some of the quiz answers. Next week, we're doing predicate logic. Anybody in here remember what the word predicate means in English class? Grammar? What is it? Anybody? It's the action part of the sentence, the verb, the adverbs. That's the predicate. We have the subject and the predicate, remember? The subject is more the nouns. Oh, the nouns, they're kind of like true or false, aren't they? Kind of like propositions. Predicate talks about conditions and actions and relations. And there's a whole logic built around that, but it uses this as the basis. So we're going to be talking next week about predicate logic. It gets a little deeper, but wow, is it really associated with programming? Because with programming, you are examining states of being, relations between things, if they're equal, if they're not equal, if the student is enrolled or not enrolled. All these kinds of things are in your software. So predicate logic is an important topic for computing. Okay, so who brought in questions on the quiz? Anybody? Wow. So you feel like, is that a question?
Yeah, I can get number 9.
Number 9? Okay. Anything else? Is that the one about the axiom on 75? Yeah. And I'll tell you what, when I read those the very first time, they were written by the dean at the time. I tried to do them in my head because I thought, gee, I know this stuff so well, I could do this in my head. And the more I tried it in my head, the more confused I got. So it's worthwhile knowing how to really do this with logic. What it is an argument. And when you get an argument, your test is for validity or invalidity, okay? Validity says that this argument is always true. This conclusion follows from the given statements. And so what we need to do is look at the given statements, build a truth table from them, and then only examine where they're true. Because the argument is only valid if you assume the first 2 statements are true, and then see if the conclusion follows and is also true. Does that make sense so far? That's the strategy. So now let's see how to do it. Let me get it back up on the screen here. read that back? Yes? Okay. All right, so what it says is, when taking the question, it would appear as, okay, use truth tables to determine whether the following argument is valid. So valid means taking the given statements and seeing if when they are true, the conclusion is also true. So what are the given statements? If there's a tractor-trailer accident on I-75, Highway 41 is blocked. Highway 41 is blocked. Therefore, there's a tractor-trailer accident on I-75. When you first look at that, you say, well, that sounds pretty valid, right? Well, let's see. So, we basically have two basic propositions. We did number 10 last time, we had 3. For this one, there were 2 basic propositions. Anybody know what they are? Accident on 75 and 41 is blocked, right? So let's use A for accident and B for blocked. How's that? Now, if I have 2 basic propositions, how many rows do I have in my truth table? 4, right? 2 to the power of how many? So 2 to the second is 4. So I will have 4 rows. So I'll have T, T, F, F, T, F, T, F. And this gives me every combination that they can be for the truths and the falses, right? Now, beyond that, I only have the if statement, don't I? And it says, if A, then B, right? If there's an accident on 75, then Highway 41 is blocked. So, when is an if statement true? Well, we can say it's always true except when you have a true implying a false, right? So, true implying a true is true. True implying a false is false. False implying true, this is the one that's hard for us to get our arms around, but because if we start off with something that's false, we don't know what it'll cause. We have to assume true. Or we can use the definition of this, which is not A or B. That's the definition of the if statement. Because notice the if, the arrow, was not one of my operations when I showed you the 5 rules, were they? Was it? So therefore, it has to be defined some other way. It's actually defined from the or statement. Okay. Now, in order to conclude that there's a tractor-trailer accident on I-75, I must look at where the if statement and the block statement are both true at the same time. Well, they're both true right here. Nope, I'm sorry. Let's go over here. Looking at the if statement and the block statement. They are both true right here. They are both true right here. Okay. T and T, T and T. Is that okay so far? Now what I have to do is say, in both those cases where they're both true at the same time, is there an accident? Well, let's see. Here, this row, there's an accident, isn't there? This row, no accident. Now, let's look at it from the logical point of view, or from our own building it. Could 41 be blocked because there's construction on 41? Could 41 be blocked because there's a lot of traffic on 41? So there's not always an accident on 75, is there? So therefore, it's not valid. So if you were to walk out of here and start going towards the interstate and finding 41 is blocked, is it fair to turn to whoever's with you and say, uh-oh, we can't take the interstate because there's an accident? No. And you see how logic worked that out for us. Did I help you with the problem?
Yeah, I'll see what I did wrong. Thank you.
Okay, great. But you see how that's, you can use this to have fun with people when you're partying or having, and they'll say a couple of things that you're gonna say, that's ridiculous, but you don't say that to them, because that starts an argument, doesn't it? So what you want to do is say, well, let's assume that that's true. Okay? All you need to do is come up with a case where their conclusion could not be when their statements were in fact true. Make sense? Okay? That may get you in trouble too, because it frustrates the other person, because then they know they're wrong. Yes?
I need some clarification on this. So on the far right column, if it's true, that means 75 is blocked, right? On the far right,
This is there is an accident.
right? So on the far right, on the very last
Oh, over
column
here,
with AB,
yes.
yeah. So true means 75 is blocked, right?
Over here.
Over there. Okay. So what does the true mean
This
on the far
means,
side?
this says if 75 is blocked. So if there's an accident on 75, 41 is blocked.
Okay. So how?
Okay? So sometimes there's an accident and it's blocked, and sometimes there might not be an accident that's blocked. Okay?
So how do the two falses on the bottom come out to?
These two?
Yeah.
So here's a case where it's true that if there's an accident on 75, 41 is blocked, but 41 is not blocked. Blocked, false. 41 is not blocked. Okay, and here's
Oh,
an
I see.
interesting one. This is answer to number 10. Okay. Number 10 was exactly the opposite. It said, if there's an accident on 75, 75 is blocked and 41 is blocked. But then they really never dealt with the 75 is blocked part. It's kind of an interesting one. It was kind of like thrown in there to complicate it. Because really what they said then second was 41 is not blocked. And then their conclusion was there is no accident on I-75. Now, if I told you definitively, if there's an accident on 75, 41 is blocked, and you said that, you took that as a true statement, right? Then you couldn't have this one, could you? Right? Because you took this as a true statement. So you can only look at these. All right? And then you find out that when that's true, this one's false. I'm sorry. That's it. When this is true and this one's false because it's not blocked, that's what you really want to look at. Because I didn't put the not be in there. If I put the not be in, it'd be a little clearer, so let's do that. So this would be false, true, right? So now number 10 would be looking at where this is true and this is true. Because if there's an accident on 75, 75 is blocked and 41 is blocked. You could simplify that to if there's an accident on 75, 41 is blocked, right? So, where this is true and this is true is right here, isn't it? That's true, that's false. It's true, that's false. It's true, that's true. It's right here, isn't it? And there's no accident on 75. Because 41 is not blocked. Okay? Does that help?
Yes.
So the validity argument is not arguing about whether or not the given statements are true or not. It's whether the third statement, the conclusion, follows. Meaning that if those first two are true, is the last one also true? Does that make sense? So, that's both 9 and 10, isn't it? All right, any other questions? Any questions about the course in general? Does everybody see how it flows? So we basically are trying to do about a module a week and the quiz. Now there are a few modules, let me bring those up so we don't confuse it. So looking at content, right now we are on Module 2, Logic and Propositional Logic. Next week we're going to do Predicate Logic. Now once we finish that, we will have finished the lectures in class on logic. We have a couple of other modules which are very good for you. Logic in Computing talks to you a little bit about how this works in the computing world. So I'm not going to lecture on it because there's just some good articles in there I want you to read, right? Because what do you really want to get out of this course? What's the relevance to what I'm going to do in my career? That's what you want out of this course. A lot of that's right there, but it's a reading thing. Program correctness also talks to that because a lot of times the correctness in your program is because your logic flow isn't logical. Okay? That's also a reading assignment. The other thing you need to know is if you're running behind, get caught up by the next week because then the first test comes up. So the first test is going to be over propositional and predicate logic. And that'll come up week after next. The next thing we're actually going to talk about in class is complexity analysis. So it's not till Module 7. We're going to skip some for your reading. Okay. But complexity analysis is the basis for your project. And I think I asked earlier, Monday maybe, how many in here have heard of the big O? Yeah, a number of you have been exposed to it. And that's complexity analysis. So we're going to talk about that, and then we're going to have a project that you're going to do. It's an individual, it's not a team project, of where you're going to go actually take two programs with the same complexity analysis, or two algorithms, and program them and compare them with actual data, chart them with a graph, and then report back what you found and why you think you found it. If they came out the same, they came out the same because they say big O, right? But they won't. So you want to find out why they didn't come out the same. And then we get into sets. And this algebra that I showed you today, which is the common algebra from among all algebras, I may bring that up again because the algebra of sets, union and intersection, are also the two operations of that algebra. And it works the exact same way, commutative, associative, distributive, converse, and identity. And the interesting thing is that when you see the definition of those operations, they are not just given operations, they're defined in terms of propositional logic. So I'll show you that when we get there. And where logic teaches you how to think in terms of the way that programs think, because they are very logical. Sets help you think in terms of how data is stored and how you retrieve and how you set up databases, for instance. So set theory, or sets, is data-oriented where logic is program-oriented. Then we're going to talk about relations and functions. But you're going to learn about relations anyway in predicate logic next week. But we'll then formally talk about the properties of relations. And we'll talk about the properties of functions. But we're going to talk about relations in terms of actual things, like parent-child, brother-sister, those types of things. And it brings it alive. It says, okay, that's what a relation is all about. Not in terms of numerical math, but in terms of what we're doing, which is actual data. We're going to talk about graphs, and those are not XY coordinates. Those are pictures. But they're pictures, it could be a flow chart. That's a graph. Yes, sir. Ooh, everybody drop their keys? Check your pocket and see if you're missing your keys. Just out in the hallway. There's probably somebody that sat down in the hallway waiting for class and got up there. Well, they move on. So anyway, relations. Functions then are actions, one to another. I'm sorry, graphs, what we're talking about. They're pictures. But when we get past graphs, we're going to talk about a particular type of graph called trees. So how many know about binary trees and binary search, right? Yeah, you've heard that before, right? We're going to relate that to all of what we've done. Right? So it all builds on that. And when you begin to understand trees, that's what you need to know to understand databases. Combinatorics deals with some methods for analyzing data. By the way, my nephew's wife is a data analyst. If you want a job like that, lots of money, become a data analyst. They moved from Florida to New Jersey because he's doing postdoctoral work at Princeton. Which that sounds great, right? But you're not going to make any money. It's kind of like being, well, kind of like being a graduate assistant. Okay? I hope I'm not I'm trying to disparage being graduate assistants because I was one once. But it does make you a lot of money. But she spent 2 weeks, I think, and had a very large paycheck offered to her by a major corporation up there in New Jersey. They just can't find data analysts like she is. And combinatorics is going to be the basis for analyzing data. Now, my module is not going to get you the big paycheck, but it may give you enough of a flavor for what it's all about that you might want to say, gee, maybe I ought to look at that. And I don't want to lose any students for the College of Computing, but Coles College has information, what do they call it? It's IS, Information Systems. Yeah. And I think they talk about that in Information Systems. But at any rate, and then after that we have a short module on proofs, of which your third test has 2 or 3 questions on proofs. Kind of tells you how much importance I find in proofs. And yet I spent 6 years studying proofs, because that's what a theoretical mathematician does, which is what my degrees are in. But I spent my life in software, and so I know the difference. And I want to get to you what you need to know to be very successful in computing, and not keep it a secret by burying you in proofs. Okay? So does this make sense to you so far? You know where we're going and why we're going there. So please, as we go through this, make sure you're doing the quizzes before the first or second meeting of the week, because the first meeting will be where I talk about it. And if you get bogged down by other studies, just make sure you get them done before the Friday of that week, because I'll answer questions on the quiz on Friday as well. And that way, that gives you 2 or 3 exposures to the same knowledge and hopefully burns it in. So at the end of the week, you're going to say, I understand this stuff, I got it, I'm ready to move on. But I didn't get it because I want a grade, I got it because I want to get it, because it's going to mean something in my career later on. Okay, any last comments or questions? How are we doing? We're right on time. Okay, then I will see you Monday.